So thank you. I would like to start thanking the organizers for the for putting together the conference and for the invitation to talk about our recent work. I will talk about the correlated state of which appear in trilayer ABC on hBN. And this is a work that I've done in collaboration with María José Calderón from Instituto de Ciencia de Materiales de Madrid, my same institute, and with Alberto Camjalli from Universidad de Buenos Aires. Okay, so this has stopped working. Let me just somehow share again. Do you see the screen now?
Yes.
The mute again? No, okay. So, okay, so now it works again. Okay, so well, we have seen all the plethora of correlated states that appear in TYC graphene heterostructures, from superconductivity, spin valuabilization, nematic states, topological states. But well, we know, and it was realized from the very beginning, that a Moiré structure can be obtained not just twisted, but also from lattice mismatch. And in particular, it was early on in already very soon after the insulating and superconducting state in TYC graphene were discovered, in which the group of FEM1 in Stanford designed a device in which they had ABC trilayer in between two gates, and so also observe insulating states at interior furnace. So this is the system in which I'm going to talk about. So I will start just introducing it more carefully. So, well, we start from a trilayer, ABC trilayer graphene, and here ABC is associated with the stacking of the three layers. So already even without the Moiré, so here the layers are quite flat, because so without the trigonal warping, they are like half a cubic dispersion. When the boron nitride is put, it's aligned with one of the layers. So we have this Moiré heterostructure with a lattice constant, which is around 15 nanometers, very similar to the one in TYC graphene. And so these bands are folded in this mini Brillouin zone. And so we can see here that the first bands are quite flat. So here I have only plotted a single valley, but there are two valleys are related by, which are related by time reversal symmetry. If an electric field is applied perpendicular to the heterostructure and there is a voltage drops here, so there is a gap which opens here at charge neutrality. And so in the Moiré system, the valence band becomes isolated. So here this valence band is isolated and quite flat, and so it will be have quite a tendency to show correlated states. Well, so this is the system that, as I have mentioned before, it was created, the device. So there is a top gate and a bottom gate. So this is the trilayer, and it's aligned with one of the boron nitride substrates. And so with playing with these two top gates, it's possible to tune on one side the band structure via this gap opening. And so depending on how large or how small is this electric field, so this band will be modified, but also the doping. So you can see here that the, so here in this direction is, so the doping is tuned, and so here the valence band is studied, and here is the conduction band. You can see that the valence band is much more correlated. So also you can see here, so in this direction, one is changing the sign of the electric field, and you can see that there is a clear difference between a positive and a negative sign. In fact, in this system, interesting aspect of this system is that depending on how is the, so whether the boron nitride is aligned with respect to the bottom layer or with the top layer, and playing also with the sign of this electric field. So this valence band can be trivial, so topologically trivial, or it can be topological. So these two sides correspond here to the trivial part, so to the trivial case and to the topological case. So the system I'm going to focus, the situation I'm going to focus is the case in which the bands are trivial. And so in particular here, it was observed that there are insulating states at both quarter filling and half filling. So this means one hole, so doping from here, or two holes. So two holes here is half filling because we have these two valleys. And here there has been, from the very beginning, the question of whether these states are correlated Mott insulating state, or what and which kind of symmetry breaking one can expect. And so this has become now even more interesting, having in mind that there has been some experiments in the ABC trilayer without the Moiré, in which similar physics is observed. In particular, what is observed is ferromagnetic states that seem to could be even just stoner ferromagnetism. So it has been proposed that in the Moiré, what is happening is the same. So somehow, so what I'm going to do is I'm going to study the system. In particular, I'm going to look at what kind of features one can expect coming from the Mott physics in such a way that then possibilities can be compared to other explanations. So well, to study the system, I'm going to start from a lattice model for this valence band. So this lattice model, so it's based on Moiré, so invariant function for the Moiré, okay? And it was proposed by Sang-Sentil a couple of years ago. So, so we have a kind of two orbital model referring to the two valleys on a triangular lattice of this Moiré. So in this, for these invariant functions, so there are the hoppings are sizable up to at least the fourth neighbor. And so the two valleys are related by time reversal symmetry, and these hoppings are complex. So well, the bands and both the bands and the hopping parameters are going to depend on the voltage. Well, in most of the cases, except that I say something in particular, I'm going to take a specific value of the field, which is 30 milli-electron volts. But in principle, similar physics can be expected as far as the Bannier model is valid. I'm going to dope. So whenever I talk about doping, so I'm doping from here. This is whole doping. Okay. So well, in the same work, Sang-Sentil also did the projection of the interactions on the Bannier function, and so you can see what kind of interactions are present in this system. There are density-density interactions, both the typical on-site Hubbard interaction and also interaction to first nearest neighbors. These ones are sizable. And then there are smaller terms, which can be whether the on-site was coupling, first nearest neighbor direct exchange, or even assisted hopping. Well, one can see that these values are of the interaction. These interactions are much larger than any other terms, quite much larger. So somehow makes sense to start from this, a model in which there are only density-density interactions, and then later, once this model has been studied, to see whether the other terms can modify the picture or not. Well, in reality, I'm going to, so in principle here we have first, so on-site interaction and first neighbor interaction. I'm going to simplify a bit more the model. So it's known that if there is no charge modulation, so the main effect of the first neighbor interaction can be, to some extent, at least for what regards mode physics, included in some effective Hubbard model. So this is, of course, not exact, but it can give a reasonable point of view. So the effective mode U that one can expect in this effective Hubbard model that I'm going to use, it will be smaller than the on-site, the Hubbard on-site, but larger than the on-site minus the first neighbor. I'm going to study this system with dynamical mean field theory as implemented in the Rutgers code. And so this technique has been widely allowed in mod systems, including cuprates, iron superconductors, or many oxides. And I'm going to focus on the specific case of 2 holes per Moiré unit cell, so in half-L. Okay, so let me first look at what happened when there is no symmetry breaking. So in the first part of the results, what I'm going to do is I'm going to enforce that there is such a lack of symmetry breaking, okay? So the first thing that we are going to see is how the spectral weight is expected to reorganize. So here you can see this is the non-interacting band. And here I'm going, all the time I'm going to plot only one of the values. So the other one will have the same physics, but just time reverse, or can be obtained by time reversal, okay? So now what we are going to do, I'm increasing the interaction, so of this effective Hubbard model, and you can see how there is this, so there starts to be some spectral weight that goes away from the band. So it's already observable at 5 milli-electron volts, and of course it becomes larger when it's increased. So this the band. So it's also, we can see that this part that stems from the band, it starts being renormalized. And in particular, it becomes narrower, as this has been observed in other mod systems. So somehow is that the mass becomes higher, but you can see that this is not just, what we observe is not just as simple as making this band narrower. So it's a bit more complex here. So this reorganization. So if we continue increasing more and more value of U, so these effects become more prominent, and you can see here how this band becomes really, really thin, and how really most part of the spectral weight has gone already away, has become very incoherent, and it's forming the Hubbard bands. So this here we're still in the metallic part and increasing a bit more the interaction. There is transition to a mod state where all the spectral weight is at the Hubbard band, and we don't see anything here at the quasi-particle band, at the renormalized band. So an important aspect here, so if we just consider the values that I have mentioned before, we will expect to be somewhere here. I was talking about 25 milli-electron volts, but I don't want to really, so there are really uncertainties on the values of the interactions, both from the values of the screening, from the fact that they come from the band structure, this also, there are different band structures that can be So it can be different. So it's not necessarily have to be exact like this. So I'm going to, as I say, consider this as a parameters to study the phenomenology of the model. Well, you can see that we see what I want to call your attention here is like, so here, even if we are at an interaction which is already quite far from the mode transition, this is around the half. So there is a lot of the strong modification of these bands. So a lot of the spectral weight has become incoherent. I would say around the 60% of the spectral weight is not in this quasi-particle band. So we expect this to have a strong effect on the density of states. And in particular, well, so this is, so now I'm going to be in a region close to here. So this is the non-interacting density of states. And you can see, well, it's not surprising that the interactions are modifying strongly this density of states. We can see how all this part has become here very so much narrower, and also the shape is kind of different. Here, this is the emergence of these Haber bands. There is also expected, we also expect even when we are in the metallic state, we also expect to have dope independence of this density of state. You can see that this is not a rigid band shift. And also there can be some temperature dependence. So when we are very close to the mode transition, here mode transition is at 28 millielectronvolts. So, and here I'm considering 23. You can see that, well, when we are at low temperatures, so we still have this system is metallic, and we have here this renormalized band. So this is to be compared with this non-interacting band. And this is the density of state here in black. But now we increase the temperature, and the close to the mode transition, this quasi-particle band will be kind of melted. So the system becomes more incoherent. So the main message from this is that, as it has been also found in other mode systems, if we are relatively close to the mode system here in Swiss bilayer, and we expect to have a quite renormalized density of state and a spectral weight. So and it can be even insulated. Okay, so let me now go to the ordering. So while we know, it's well known that if we have the Haber model and we are close to the mode transition, there is a tendency towards ferromagnetism, antiferromagnetism, sorry. We have a triangular lattice, so the standard nil state is frustrated. There may be some other antiferromagnetic state, nevertheless. But also, particularly in this system, so we have a lot of hoppings. So it's not just hopping to first nearest neighbor, we have hopping to many neighbors. So there can be also different antiferromagnetic states. In fact, there was a work last year on the order states in this trilayer system by Chimiausi and co-workers, and in which they found an antiferromagnetic state that breaks C3 symmetry, and that seems to be stabilized by Hund's coupling. So in their calculation, they do most of the calculations at Hund's coupling, which is of the order 0.05 times U. So, well, the one that we expect that much smaller. And in particular, they compare some state, the energies of some state, and they find that this state, which is it is kind of a stripe antiferromagnetic spin order. So it is smaller in energy than this, the state with no order, or also that state in which one consider similar ordering that of the valley. So here, now, however, if you look at the, look at this picture, so what it seems is that it's really Hund's coupling what is creating this state. So, so somehow, as I said, we expect much smaller Hund's coupling, and we in fact are starting from 0 Hund's coupling. So just from this, we will probably think that we were not going to get some or any ordering. So as I said, we have this Hund's coupling equal to 0. Our interactions are spin valley symmetric. The bands are not, in the sense that the two valleys are related by time reversal. But then we find an order state. We find it close to the mode transition. As you can see here, this is mode transition, and this is the region where we find it. The order parameter, so what we are looking with this technique, with dynamical mean field theory in single site, is local physics. So the order parameter is the polarization that we have on site, okay? And in our case, what we are finding is that it seems to be degenerate the state in which we have polarization of the spin or polarization of the valley. We have done most of the calculation assuming given freedom for having a valley polarization, but whenever we have done the calculations assuming that the system can just polarize the spin, or whether allowing all the freedom, we are getting the same energy. So somehow it seems to be degenerate. So then we, okay, so it's, so somehow it seems that they are degenerate. We cannot see exactly the pattern with this technique, but we have reasons to believe that this is the same order that they were finding. We find this order at other values of the electric field, but not if we just consider a simple 2-orbital triangular Hubbard model with hopping to first snare. So this state seems to be very much linked to the mode transition, not just an interaction, but also we find it's only very close to half-Ellen. And it seems to survive up to temperatures of the order of 3 Kelvin, which is consistent with the difference in energies that we find. The system, if we are below the mode transition, seems to be slightly metallic, but this is not necessarily Fermi liquid. And we find that even if the difference in energy is quite small, we can find a spectral wave organization in a larger energy window. So let me just say, end with this slide. So before I have said that, okay, so these terms are the most important ones, the density terms, and with these effective Hubbard models, we have found that there is this kind of anti-ferro order spin or valley. Now, we have seen that there are other terms here, and if we compare this energy, so the difference in energy, so we expect if we have, for example, from the on-site Hund's coupling that Chimiao co-workers were introducing, we expect that this will favor spin ordering versus the valley ordering here. But what seems to be more interesting is that it's this direct exchange. So the values of this exchange are similar. They can be even larger. So in normal situation, one can find even ferromagnetism. So, but so the main message from here is that, okay, the system can order antiferromagnetically in principle. So these differences in energy are small, and so they can be compatible with external energy. So there are even the possibility that different states appear or can even tune by strain screener or something like in a similar way in which it has been found in Swiss Valley graphene. So just a reminder that even if what we find is the exchange, so if we are not very, very far from the mode transition, we expect to have a renormalization of the spectral weight. Okay, so thank you.